Hey everybody, this is the AB review limits, just kind of getting us started and remind us about some things that we're going to need to use this year and kind of get the ball rolling a little bit. So the first thing I want you to do is to make a list of strategies that you might use when calculating a limit. So I'll let you think about that for a little bit. Maybe perhaps press pause and just see if you can think of many of the things that we did. Again, it's okay if you don't think of all of them, and I probably will forget as well some of them, but go ahead and try to think of some of those. And then I'm going to get my pen out here and we're going to start to make a list as well. Okay, so some of the things I just want to highlight here are, remember sometimes they give you a limit, but it feels like it really actually shouldn't be a limit, so you can just substitute the value in easily. So I'm going to put that on my list. We can substitute. There's always some sort of algebraic manipulation we can do. That includes things like factoring, rationalizing. A lot of times it's the numerator in calculus for some reason. Let's see, what else could we do? I think those are the big ones I'm thinking about. So factor, rationalize, cancel, do that kind of thing. A lot of people want to use L'Hopital's rule, which is great. Remember, we don't learn that right from the beginning just because we don't know the derivative. I'm going to use the, I guess it's technically the true spelling is hospital. L'Hopital's rule. Remember, this only works in certain situations. In AB, we talked about it being a 0 over 0 or an infinity over infinity situation. There are other ones that we'll run into here that we'll see, but those are the main ones that people will do. There are other things where we're not doing like doing math work, but we're analyzing something else. So we're like on our calculator and we look at the graph of it. Sometimes they give us the graph and that's how we have to do the limit. Sometimes looking at a table of values. Sometimes that's good. Remember, we want to look close and we want to look from both sides. For students who haven't had me, I use what's called the drunk test. So imagine you have to take your finger, your left finger, index finger, and your right index finger, and we have to make sure that both of them touch your nose. Okay, so that's what I call the drunk test. We want to make sure that we check from both sides that it's the same thing. We can also use our calculator to plug in a number that's close. So it's sort of like substituting, but plug in a number. So if it's infinity, we can just plug in a really huge number. If we're trying to head toward 2 and we know it's not going to work, we can try 2.001 and 1.999 and see if we get the same result. And again, think about that drunk test that something's happening from the left and from the right. That's the same. Okay, so just some quick examples that I want to go through with you. So my first thought on example 1 looks like we could factor it. It may or may not be helpful. If we're writing out here mathematically, we should keep writing the limit until we've actually figured out what our answer is. Certainly on a free response, we would want to make sure that we continue that good notation on a multiple choice. Obviously, they're not checking our work, so if we don't do that, it makes sense. So I factored there. I've gotten rid of my problem, meaning plugging in a 3 now that I've factored and canceled is no longer an issue. So I get 2 over 6 or 1/3. Remember, 2 over 6 is completely acceptable on the AP exam. Example 2, trying to plug in 3, I can tell right now that I would get a 0 over 0 situation. So if I didn't use L'Hopital's rule, what I would want to do is rationalize the numerator. So I'm just going to mention that. I'm guessing most people would choose not to do that, but I'm just going to talk about it. So what that means is we would multiply top and bottom by the square root of x plus 1 plus 2. So that's that conjugate, square root of x plus 1 plus 2. Okay, so that's one option. Maybe I'll just go ahead and continue on with that, and then we'll also do L'Hopital's rule, and you can kind of decide what you want to do. So when I multiply these two, what I'm going to get is a difference of squares. So root x plus 1 times root x plus 1 is just x plus 1. Negative 2 times positive 2. We're not going to have any of those middle terms because, again, it is that difference of squares. And down here, I am not going to multiply out because I'm hoping something is going to happen here that allows me not to. So I can see that at the top, if I simplify here, that ends up being x minus 3. And so this whole top is going to cancel with that. And so I'm just going to be left with a 1 in the numerator. And then plugging a 3 here is no problem. So square root of 4 is 2 plus 2 is 4. So that's one option. We could also do L'Hopital's rule. I like to write a little LH there so that you can see that's what I'm doing. Derivative of the bottom is just a 1, so that's super nice. Derivative of the top's a little bit more complicated. Think of this x plus 1 as being to the half power. So let's go 1/2. Leave the inside alone. Derivative of the inside's a 1, so no worries about that. And then the derivative of -2 is 0. So now I think I'm going to write one more step before I try to plug in, just because of that negative exponent makes it difficult for me. So let's see here. This 2 here from the 1/2, that really is in the denominator. This root here is also in the denominator because of the negative exponent. And again, now plugging in a 3 is no longer a problem. This time we still get a fourth, but in a little bit different way. So there's our square root of 4 is 2 times 2, we get 1/4. Okay, and then example 3. On this one, remember we can think in terms of when it's heading toward infinity or negative infinity, top heavy, bottom heavy, or equal. Another thing that is helpful in determining if things are top heavy, bottom heavy, or equal is something I call NN-FEPL, and I'll add that in here. So a couple things on this. Top heavy, that result is going to be infinite, because we're going to have a really big number divided by something that's a little bit less significant. So we're going to end up with a big number. Bottom heavy is kind of the opposite. We're going to have an insignificant number on the top and a really big number on the bottom. And what that's going to do for us is get us something close to 0, something really small. And if they're equal, like it looks like this particular case is, notice the highest degree is an x squared and highest degree is an x squared, then we just look at the ratio of the coefficient. So I'm just going to write ratio there. And then we get that 5/3. So NN-FEPL. This is what we use when we're not comparing a polynomial and a polynomial. So if we are looking at the first two, we don't see a lot, but sometimes we do. So an NN really is an x to the x. So there's an x in the base and an x in the exponent. F is for factorial. So I can kind of write that under here, I guess. X to the x, factorial, exponential, so like e to the x, a polynomial, and then a logarithm. So this is in order from growing the fastest to the slowest. So the things on the right-hand side over at the logs, those are going to grow slowest. So they're always going to be taken over from one of these others. So if we have to deal with that kind of thing, we can decide if something is top heavy, bottom heavy, or equal. Okay, so now to some indeterminate forms. Earlier, we talked about L'Hopital's rule, and so these two are the ones that generally we see in Calc AB, the 0 over the 0 or infinity over infinity. And what you have to remember is that infinity is it's not a number. It doesn't follow the rules that we want it to. So when we do something like infinity minus infinity, we don't actually know that that's 0, because it's not just like saying 7 minus 7. Because what if one infinity is technically a little bit bigger than the other? So think if we have the whole numbers, so 1 through infinity, and then we just take out the evens. Well, there's an infinite amount of evens, but the odds would be left. So in that case, infinity minus infinity would be infinity. So all of these, all the rest of these, even though it seems like we should know the answer, like intuitively we might have a guess, and I would say probably 90% of that time that guess is going to be right, but there are just some times when, because of the way infinity behaves, we won't get the correct answer there. So this is when we would really want to use L'Hopital's rule if we see something in this form. And I will show you at least one example of one of these that turns out to be something unexpected. So I'll show you that. And just really quick, I put a picture of Marquis de L'Hopital on here. He actually did not come up with this rule, just like a lot of things in mathematics. They're named after the person who published it first. So anyhow, we're just going to take the derivative of the top and the bottom separately, no quotient rule here, and our limit will turn out to be the same. Again, we want to make sure that we have an indeterminate form, and I probably have this advice somewhere. So make sure it's indeterminate form before you do L'Hopital's, and you can do it more than once, but just make sure every time you're checking that it's in that form. And even in those ones where it's like infinity minus infinity, we really need it to be rational. We need it to be a fraction, so we might have to force it to be that way a little bit. And I'm going to see, yes, I have a couple of examples of ones that are a little bit more complicated. So I know we've already done these examples, but if we wanted to do L'Hopital's rule with them, we already did example 2 that way because I had forgotten I made it that way. But let's go ahead and look at example 1 and example 3. So again, I'm going to write a little LH there so you know what I'm doing. I'm going to continue to write the limit until I just find my answer. So the derivative of the top, the numerator, is 2. Derivative of the denominator is 2x. And now it's no longer a problem trying to plug in that 3. So we get 2 over 6, which is that 1/3 we got earlier. So example 3, again, we could think of that top heavy, bottom heavy equal just like we did before, but L'Hopital's rule kind of proves that we're right in a way. So I'm going to go ahead and keep doing this one. I'm nervous my computer is going to pause here in a second because I'm getting that weird little spin around. Okay, so the derivative of the numerator would be 10x minus 3, and the derivative of the denominator is going to be 6x. And technically I still have an indeterminate form. I have infinity over infinity. Again, most of the time we know the answer to this, but I'm just going to keep going so I can kind of prove that we were right. So now if we take the derivative again, we get 10 over 6. And now x isn't even a part of our limit. We just have 10 over 6, which simplifies to 5/3, which is the answer that we got before. So it just kind of proves we're right. Okay, we went over those tips. So let's look at some that are a little bit more complicated where we have to use those tips and just work a little harder. So these are more like BC style, where those earlier ones were more like something we saw in AB. So this example 4 here, I have to make it into a fraction is kind of the big deal here. So I think the easiest thing to do is to put this x right here to make it the fraction. So I'm going to do natural log of x over 1 over x because I could flip that and multiply if I wanted to. So now if I do L'Hopital's rule, by the way, that plus is there because natural log doesn't exist beyond 0 over there. So natural log of x, its derivative is 1 over x. I'm going to think of this as x over 1, or x to the negative 1, sorry. The derivative of x to the negative 1 would be negative x to the negative 2. So let's just simplify that a little bit, and I think that that's going to help us find the answer to this one. I should have talked about what form this was, and I'll do that here in a second when I'm done writing. So 1 over x over negative 1 over x squared. And if we flip and multiply that, so that's really negative x squared over 1, we get limit as x approaches 0 from the positive or the right-hand side of just negative x, right? Because I flipped that there and x's cancel, and so I just get 0. So let's talk about a couple things. I should have mentioned before that this is a 0 times infinity form because natural log of 0 is infinity. So we might have guessed it was 0. It did turn out to be that way. Remember me telling you 90% of the time you'll be right. So if you had to take a guess, you can do that. And then again, we just created it into a fraction so we could kind of get to that answer at the end. Okay. So there's my not responding. Oh, there it comes. Okay. So example 5, this is going to be infinity minus infinity. So there's a couple things we could do, but let's go ahead and change this into a fraction first before we start L'Hopital's rule. So secant, remember, is 1 over cosine, and tangent is sine over cosine. So again, I'm going to say that and then write it as they were both a cosine in the denominator. This is 1 over cosine, and this is sine over cosine. So we would want to verify this right now, that that fraction is still an indeterminate form. This is 0 over 0 now. So we can kind of know that we could do L'Hopital's in that way as well. So our limit, and the derivative of 1 is 0, and derivative of sine is cosine, but there is a subtract sign in front of it. And then the derivative of cosine is negative sine. And so again, sine of pi over 2 is 1, and cosine of pi over 2 is 0. So we would just get this 0 here. So again, like maybe we expected, infinity minus infinity, we got a 0. Okay, example 6 is going to take us a little bit more work because it has an exponent there, and the only way we can really get rid of exponents is to use logarithms. So I'm going to start by just calling this a y equals. This, by the way, is a 1 to the infinity because we have an asymptote at 0. So 1 to the infinity, we maybe would guess 1, because 1 to almost any power, at least that we've learned to up until this point, is a 1. All right, so what I'm going to do is I'm going to log or natural log both sides of this. Okay, I just have to remember at the end that I have to kind of undo that because it's going to be the natural log of y, not the answer I really want. So what that's going to do is going to create this limit as x approaches 0 from the positive of natural log of all this mess. And remember what logs do that's really awesome is it means we can take this exponent and turn it into a coefficient. So now it's not in the exponent anymore, so I should be able to kind of manipulate it a little bit. So let's do this. Let's go limit as x approaches 0 from the plus. I'm going to have this natural log of 1 plus sine of 4x in the numerator. And this is a cotangent. So I'm going to put a tangent down here. That's how I'm going to make it into a fraction. All right, so let's do L'Hopital's rule now. So for natural log, 1 over the stuff, that's how I say it at least, 1 over the stuff times the derivative of the stuff. So cosine and then 4. So 1 over the stuff times the derivative of the stuff. All right, and then the derivative of tangent is secant squared. And so now let's look. Can I plug a 0 in now? So sine of 0 is 0, but that's not a problem here. We get 1 over 1. Cosine of 0 is 1. So we're going to get a 4 in the numerator. Secant of 0, well, remember secant's 1 over cosine. Cosine is 1, so this would be 1 over 1, but then squared. So I think for this answer, we get 4. Now remember, y is the limit I was really interested in. So this is really ln of y equals 4. It's funny, I changed colors. It didn't want to change with me. Okay, so then if I e both sides, I get to my answer, which is e to the 4, which is a really bizarre number. If you graph this, let me see if I can go grab my calculator really quick so we can see that, because it is really strange. So if we graph that, we will see that this happens. But remember earlier, while my calculator is trying to open, we had a 1 to the infinity, and we were assuming 1 to the infinity would give us a 1. And clearly that's not happening right now, which is, again, this is like the 10% of the time where something strange happens. We'll see. I might have to just cut the video off, and you might have to go graph on your calculator and see it since mine's not opening. Maybe we can do Desmos really quick. Let's do that. Usually has a nicer graph anyhow. It's looking a little different for me today. Okay, so we're going to go ahead and graph that natural log, or not the natural log. I have to look at it again. It wasn't natural log to begin with. 1 plus sine to the 4th to the cotangent. I think my computer is just upset with me after doing all that stuff on Word. Okay. So 1 plus sine 4x to the cotangent x. And again, we were really interested in what was happening at 0. If it will let me, it's not wanting to do anything right now. There we go, we're zooming in a little bit. Okay, let's see if we can get this to work. So I'm just gonna go a little bit to the left of 0. Maybe if we do negative 0.5, we'll see if that's to 0.5. And then we're gonna go, I guess that's fine. E squared, probably pretty big. Yeah, I'm gonna pick 60 there. Okay, so you can see here that this thing is looking like we're crossing that 0 right at that spot. And I don't know what e squared is off the top of my head, but you can check that on your calculator. So we can see graphically that we're proving that we're right, but it just seems so bizarre because it's not intuitive at all that that would work out that way. Okay. So try to think, if you would, before you wrap up here, try to write down an example for yourself where you could use L'Hopital's rule. So go back up and look at the different forms that you can use, like a 0 over 0 or infinity over infinity, and then an example of where it would not apply. So these would be anywhere you don't get the 0 over 0 or infinity over infinity. One bit of advice I could say is if you get a number over a 0 or a number over infinity, those would be more times where we could not use L'Hopital's rule. So if you're looking for some help finding an example, you can do that. Okay, get to the homework and you can let me know if you have any questions.